Uh, Good morning, everybody. I had trouble starting the video, but it's functioning right now. We'll start immediately by sharing the screen to where we stopped the last time. And at that time, we were talking about fusion systems in general. And we started looking at the second option for fusion, which would be magnetic confinement fusion. We identified the magnetic confinement devices that are under consideration, the tokamak and the stellarator. I showed you pictures of examples of the tokamaks, and the tokamak that is one that is in operation. In fact, is the one, the Tori at the Cadarache Research Center in France. This is the interior of a tokamak, the Tori Supra, it's called. You could see that a person can walk inside it. As a matter of fact, I'll see more pictures. And this is a device for the plasma heating. We need to heat the plasma. If you remember the Lawson criterion, we need to have a significant energy confinement time in the plasma. We have to have a sufficiently high density as well as high temperature. So here is these are microwave heaters to heat the plasma. The tokamak is a competing method to what's called the stellarator. The tokamak was invented in Russia. The stellarator was invented at Princeton University in the United States. And this is a typical stellarator, a magnetic kind of a configuration. You could see that the plasma would take the shape maybe of a ribbon rather than a toroidal or a torus. However, it poses advantage from the engineering perspective in that we have lots of room here in the center to provide for power conversion facilities, like a blanket to breed, say, lithium, tritium from lithium. The tokamak, because of its very compact configuration, does not have much room in the center of the torus. But there are two interestingly competing processes. The tokamak has to be equipped with what we call diverters. So if you take the stellarator, as a matter of fact, this would be a stellarator. When you have the fusion reaction occurring, deuterium plus tritium, you produce products of the fusion process, and that would be a helium, for instance, and a neutron. The neutron carries most of the energy from the DT reaction, as we have seen earlier. 80% of the energy is carried by the neutron, so we have to slow it down in a blanket and turn its kinetic energy into heat energy, as well as using the neutron for breeding tritium, which does not occur in significant amounts on Earth. And then, of course, we mine the deuterium from water in our oceans. So the product of the fusion process is the neutrons that would be slowed down in the blanket surrounding the plasma and by interaction with, say, heavy metal. Lithium is a candidate. We could use lead, for instance, but that's the lithium is ideal because you can turn it with the neutrons from the fusion reaction into tritium, and that's a fuel that you have to feed back into the plasma. But then what do you do with the alpha particles? The alpha particles impinge on the first wall, but they are in the plasma, and you want to bring in new fuel, deuterium plus tritium, into the plasma. So you have to exhaust that alpha or helium, in that case, particles from the plasma before you can start another cycle of putting in a deuterium and tritium, almost like an internal combustion engine where you inject the fuel into the combustion chamber. In that case, you want to get the alpha particles, are charged particles, if you remember, and deposit their energy on what we call diverter plates. So the diverter is a component of the reactor, in that case, that diverts the alpha particles and discharge their energy on plates, and then get the device ready for the next pulse, especially the tokamak. Tokamak is a pulse type of a device in general. All right, so as I suggested, we need to heat the plasma. The first method of heating is the fact that the plasma is a combination of ions, positive ions, and negative electrons. So it's a conducting medium. And in that case, when you use the transformer action, you are heating the plasma, the current of the plasma itself through what we call ohmic heating. So the plasma has some resistivity R, and the current in the plasma current I sub P squared here, I square R becomes heating like the heating that you get in any resistor. So the fact that the plasma acts as the secondary of a transformer provides it with heating. But it is supplemented, as I suggested, in this Torre Supra, the tokamak, the French tokamak, by antennas that can use microwaves at the same frequency as the plasma to heat the plasma. So you irradiate the plasma with microwaves. That's a second method of heating the plasma. And a third method, which is also a refueling method for the plasma. How do you inject the deuterium and tritium into the plasma? You use a particle accelerator or a particle beam, and that also contributes to heating the plasma, as well as refueling the plasma with the ions of deuterium and tritium, the hydrogen isotopes that we burn in the plasma itself. So we have three methods of heating the plasma: the ohmic heating, the microwave or high frequency heating, as well as an ion source or heavy ion beams. In that case, really is the process itself. And here is the interior again of the Torre Supra. You could see now the microwave heating antennas here. It's an antenna. And this picture shows you really the toroidal shape with some kind of a platform here for people to walk in and perform maintenance and construction on the inside of the torus itself. All right, so neutral particle beam heating, the particle has to be neutral, but to accelerate it, you have to have it ionized initially. So it is a whole process of getting the deuterons and triton from an ion source, accelerating them. You have to give them a charge to be able to accelerate them, and then you neutralize them and then inject them with their kinetic energy to heat the plasma in general. As I suggested, the plasma now in burning has a burn product as alpha particles. It also interacts with the walls of the container. So you find that impurities get into the plasma, and if you get impurities into the plasma, you can start losing the energy from the plasma through different forms of radiation, like synchrotron radiation. And in that case, you cannot perform a burn of the plasma. So in that case, you have to flush the plasma after each burn. And in that case, we mentioned the diverter. More detail about the diverter is shown here. You shape the magnetic field of the plasma by the positions of the magnets surrounding it in such a way that you create some kind of a cusp here where the alpha particles, charged particles are concentrated, and then they hit a plate here that you have to cool maybe with a liquid metal like lithium. And this shows actually the Alcator C tokamak. This is a tokamak built at MIT. This shows us the plasma shape again in the form of a torus, and the diverter at the bottom left here is shown. I'll show it in more detail later on. And you could see the interior of the torus with a gentleman here working on the plates that compose the first wall of the reactor. Notice that notice the gentleman here to give you an idea about the size, but there isn't much room on the inside of the tokamak. So engineering-wise, engineers would favor the stellarator because there is more room to have a blanket and coils and all kinds of power equipment in general. This is the shape of what you see as a plasma when it is in operation, a beautiful bluish color. This is the SDEX-U plasma. And what I'm showing you here is those diverter plates. So the alpha particles and any impurities now impinge on that plate, and those plates have to be cooled because you can reach really very high power fluxes, like in the maybe 1 megawatt per meter square. This is a tokamak at the Max Planck Institute in Germany. Plasmas are very hard to maintain. The magnetic field exerts a pressure on the plasma, and it acts like a balloon. So if you squeeze it in one spot, it inflates on another. So these are called the plasma instabilities. Only a configuration where the magnetic field has a positive curvature towards the plasma would make it stable. And I think I show you such a configuration, a cusp configuration in the case of the gamma, in the chapter on gamma rays and how they can generate cosmic rays in the giga electron volt energies in general. So here you find that there is a large number of instabilities. That's a challenge for people designing those devices to keep the plasma stable. Because if you get an instability and the plasma kinks, for instance, it would hit the wall. Two things will happen. It will lose its kinetic energy, so the fusion reaction would stop occurring. And the second thing is that you can have a hole in the container, and both of these processes are undesirable events. The choice of materials, of course, you need materials that can take very high temperatures on the first wall, and the high energy fusion neutrons cause radiation damage. They penetrate the first wall and the blanket. Blanket is where the neutrons interact with the lithium to generate the tritium, and they also lose their kinetic energy. That's where they deposit their energy. In fact, you'll find that some materials get activated, meaning that they become radioactive. And so in reactors using deuterium and tritium, or deuterium and deuterium, some form of radioactivity is formed, but it is not the same as a criticality process that can happen in fission reactors. So we can live easier with radioactivity being generated in fusion reactors compared with the criticality that can cause really an increase of power in fission systems, the criticality effect in general. There are lots of magnetic fusion experiments that are under consideration today. Some of you, as in the engineering profession, mechanical, electrical, chemical, can find themselves involved in developing a new source of energy. One of the early tokamaks is the TFTR, the Tokamak Fusion Test Reactor. It operated at the Princeton Plasma Physics Laboratory from 1982 to 1997. I am elated to suggest that I took part in the design of the shielding of the neutron beam. There is a report from the Oak Ridge National Lab where, as a group, we discuss how to shield against the radiation that is generated when they started burning deuterium and tritium, but they kept burning deuterium plus deuterium because it produces less radioactivity. You could see here the toroidal shape of the device, and this is a plasma while it is in operation. So the TFTR was one of the first devices ever. This is what it looked like with the neutral beam injectors here and the different nightmare of piping, but in the center you have the transformer, because the tokamak is really a giant transformer in general. The TFTR became one of the first devices ever to operate. The Europeans also have been contributing in building tokamak devices. JET stands for Joint European Torus. It was a tokamak, and it attained only a factor of 5 short of the ignition criterion. So the ignition criterion is when we start getting more energy from the plasma than what we invested into it. This is a picture of the Joint European Torus. At that stage, it's still an experiment, and you could see here the size of it relative to the standard man in the drafting process. The plasma, as you could see here, is shaped by the coils, the magnet coils around the plasma here, coil P3, coil P4, coil P5, in such a way that the alpha particles being charged are directed onto the diverter, and the diverter is where the alpha particle deposit their energy and are released out of the plasma. And then, of course, you inject now the fuel from neutral beams into the plasma. Notice that to shape that shape of the plasma, not really in a directly circular fashion, you have to have magnet coils that go all around the periphery of the device. This is coil P2 toroidal, and these are the toroidal coils. These are the magnets that maintain the plasma in the center, but those little ones here are diverter coils. They designate them as D1, D2, D3, and D4. They give that shape where the alpha particles are dumped on the diverter plates, and the energy in them obviously is extracted in that case, as well as being products of the fusion process. They are exhausted from the plasma itself. So there is progress going slowly. This is the JT60 tokamak, and that one prominently shows the NBI. NBI stands for neutral beam injector. You could see they're huge here, and you could see that the plasma is shaped also so as to get a cusp, and where the alpha particles are being dumped on the and the impurities in the plasma are dumped on the diverter plates. Around the plasma, you'll find the superconducting colloidal coils. This would be the toroidal coil, and generating a magnetic field that goes around the plasma. And then you have the plasma itself generating its own magnetic field. The magnet coils have surround the plasma, as you could see here. And through transformer action, we heat the plasma and maintain its shape, because the plasma current itself generates its own magnetic field. So you have two magnetic fields working together, one from the toroidal coils, and one and the plasma itself generates another magnetic field, the colloidal field, as we have seen in the last lecture. And that gives the particle in the plasma a trajectory that goes around the magnetic field lines in the form of a helix. And that's a way to contain it in general. Notice that we try not to use copper for the coils of the magnets to reduce the amount of energy that you are investing in creating the plasma. So in that case, those coils are superconducting. So if you use materials that are superconducting, you have to use cryogenics. You have to cool them to cryogenic temperatures to reduce the amount of energy that you are using in generating the plasma. In some companies, private companies are involved in the research field. This is what's called the doublet 3D tokamak. It is built in San Diego in the United States by the company General Atomics. It looks almost like a sphere, no room in the center. So it's a very nice experiment. However, engineering wise, how do you get a reactor and extract the energy from it with very, very little space in the center? So we are, knowledge is acquired about how to stabilize plasmas from those tests in general. The the most important effort going on today in the plasma in the fusion field is that we have to all learn about is the International Thermonuclear Experimental Test Reactor. Its acronym is ITER or ITER, whatever you like. The play is on the name ITER, which means in Latin, the way. So supposedly this is the way to reach eventually self-contained chain reaction. Their attempts at breeding, because the breeding of tritium using the DT reaction is extremely marginal, as I'll show you in the next chapter. So we need ways of generating more neutrons so that we can have enough breeding of the tritium from the lithium. One way, as it is suggested, is to use neutron multipliers like lead or bismuth or beryllium. The ITER, or the International Thermonuclear Experimental Test Reactor, is an international effort. It's involved the People's Republic of China, the European Union, Japan, the Republic of Korea, the Russian Federation, and the United States, of course, and the whole effort is under the control or the auspices of the International Atomic Energy Agency. The reactor has been built already, and it's ready for operation, and it contains all the elements for a future fusion reactor, except that if there is any criticism to it, is that there is no room in the center to have the power conversion equipment. So maybe the future experiment could think about a stellarator in that case. This would be, as you could see here, the toroidal coils that generate the magnetic field that contains the plasma. The toroidal magnets are superconducting, so they use niobium tin, 18 of them, they're wedged. Then we have some colloidal magnets, also use niobium titanium. And then you'll find one feature of the TFTR, the ITER here, is that you have a blanket module. What does the blanket module do? It contains some form of lithium to estimate how much tritium we can produce if we burn deuterium and tritium in the center of the reactor core. Then you can find here also the diverter, as I mentioned, for other reactors, where you send the products of the fusion, the alpha particles and any impurities, on those diverter plates. And it's a very difficult design feature here, because you can get very high energy fluxes impinging on it. So some people suggest using liquid lithium to cool the diverter plates in general. You have to use cryo pumps because the magnets have to be, materials have to be cooled to act as superconducting magnets in general. The ports, are lots of ports, a nightmare of ports here, 6 heating ports, 3 test blankets, and 2 limiters, and many different diagnostics for the device. So this is the diagram of that ITER reactor in general. This is a cross-section of the device, very prominently shown here. You could see the microwave antennas for heating the plasma. Also here, the diverter, where the products of the burning, remember that the tokamak is a pulse system. You generate a pulse and then you exhaust the products of the fusion, the alpha particles, onto those diverter plates and any impurities from the wall, and then you inject into it. These are the beam injectors shown here, a new amount of deuterium and tritium, and start another burn and so on. So it's almost like a pulsating, like an internal combustion device. This is the ITER facility at Cadarache, the research center in France. This is under construction, but the construction has ended and the device is ready for operation. In 2020, basically, they were starting to use first plasma. If you can read here, it says the ITER project moving toward first plasma, and you find the flags or the countries that are contributing to the effort: the United States, the Russian Federation, Japan, South Korea, and so on. All the countries, it's an international effort for the whole scientific community in the world. Okay, so what is next after the TFTR? Whatever information would be obtained, especially about the breeding of tritium, which we know is somehow marginal. The idea is to move from there to what is going to be called the demo system, where we are hoping to produce a reaction that eventually would be producing more energy out than energy in. So in that case, according to the Lawson criterion, we would be in the ignition mode, which is beyond the break-even mode. Other experiments are still also in different countries, like in the UK and Japan. The JT Japan Torus 60 tokamak is an experiment that works in Japan. You could see here, these are the neutral beam injectors. The torus is there in the center. The toroidal field has a strength of 4 Teslas. The plasma current is 3 mega amperes. It has a major radius of 3.4 meters and a minor radius of 1 meter. The minor radius is the radius at the center here. The major radius is a radius at the outside of the tokamak. So there are experiments all over the world, but ITER is a major experiment that is international in nature. A plasma that would reach break even is hoped in the Japan Torus 60. The ITER would now hopefully reach ignition. So in that case, you start producing more energy out than energy in. Once you gain the experience from the ITER, the next step is what they call the demo. And in that case, the demo would be designed according to information that we get from ITER to generate steady state electrical power, hopefully in our lifetime. The fusion power of ITER is planned to be a nominal or a design value 500 meter and 500 megawatt. It's a small t here, means it's megawatt thermal power. No electrical power is going to be produced. The demo, on the other hand, will turn the power, the thermal power into electrical power. If the efficiency is 1/3, that would be 1500 megawatt thermal in general. It is being designed. Hopefully the information from ITER will help getting it on track. This is the a diagram of the difficulty in attaining fusion under control. Is that we have to invest in heating the plasma. So we invest here in ohmic heating through the transformer action. This is the power as a function of the temperature of the plasma. But as you operate at high temperatures, you'll find that you are losing energy from the plasma through Bremsstrahlung, X-rays, for instance, generated from the electrons interacting with the plasma. Synchrotron radiation is when electrons operate in a magnetic field. And it's a balance between heating, alpha heating from alpha particles and losses from the plasma. And when you get more energy out, then that is the ignition process. Other tokamaks operate at different laboratories, as I've shown you, the JT60, for instance. In Japan, that's another tokamak, the masked tokamak. You could see here the coils, and it takes the shape of a cylinder, but in fact, it's toroidal on the inside to maintain the plasma. Some people come up with interesting ideas, like at the Los Alamos National Laboratory here. They are experimenting with what's called a magnetic flux compression generator. So they get a plasma right here, and then they're surrounded by an explosive, chemical explosive. Once they explode that explosive, they compress the plasma. As they compress the plasma, they bring in the ions close to each other to overcome the Coulomb repulsion. So you could see here this, we can say it's a combination of magnetic confinement, a magnetic field containing a plasma, but also inertial confinement, where you compress the magnetic field lines with a chemical explosive. Some people suggest a nuclear explosive, a fission process. It would be a hybrid in that case. Some individuals are also exploring ideas on their own. There are billions of dollars actually that lately, in fact, lately only, that private investors have been putting into reaching fusion. So the hope of achieving fusion in our lifetime is great. This is, as I suggested, a goal of getting a hybrid of the inertial confinement and the magnetic confinement. So you could see here, a gentleman has set up a company where he gets a vortex of a liquid metal. He creates a plasma on the inside of the vortex, which would be a vacuum. And then he uses a mechanical piston to compress the plasma in the center of the rotating liquid metal. And the suggestion here is that compressing the plasma magnetic field lines would help it. So again, it's a combination of magnetic and inertial confinement, taking advantage of both processes. And we studied magnetic confinement earlier. That process is a mechanical kind of system, supposedly. And basically you have pistons. It would be a large device with gentlemen, the standard man in drafting shown there. But in fact, here is the gentleman who have established a company. He called it General Fusion in Vancouver, British Columbia, Canada. And here is the device itself. And these are the pistons that would combine an inertial confinement approach to magnetic fusion. And the company's name is General Fusion, as you could see right here. One very interesting approach of fusion has been also adopted and invested in by the aerospace company Lockheed Martin. And you know, Lockheed Martin is a major contributor to the aerospace airplanes kind of manufacturing. And Lockheed Martin is working on an interesting fusion device. I think they are on the right approach because they have the best way of containing the plasma. I suggested that the cusp magnetic field would be the ideal way of obtaining a stable plasma configuration in the chapter on gamma rays generation, and how I describe the theory of how we get cosmic radiation in the giga electron volt by cusp magnetic fields. So Lockheed Martin somehow learned about the idea of cusp magnetic fields and has been building, in fact, the device that uses a cusp magnetic field. So you could see here that they have a coil here, a superconducting magnet, another coil here, a superconducting magnet that generates a cusp magnetic field with a plasma generated here in the center that has a positive curvature of the magnetic field. So that plasma would be stable. They heat it with neutral beam injectors and hope to get ahead of everybody else in the field. And that's actual picture of the device that they built, showing the interior of the device. That's a spherical container here with the ion beams that are heating the plasma in the center, but the plasma is now confined using a cusp magnetic field. Lockheed Martin, of course, is an aerospace company. Interestingly enough, I got an email from a student who worked on his master's degree, and then he went to Texas A&M. He got his PhD there. He sent me an email, said me he would have never thought that we'd be working on a fusion device. So I think he's involved with that project right here. I hope for Lockheed Martin to succeed in their small device. So the configuration here as a diagram, as you could see, the beam injectors that heat the plasma, one coil here and one coil there. And the plasma in that case takes the shape of a cusp, because here that coil confines the plasma in that case. So you get a plasma right there in the center that is stable as they can. Now, I think Lockheed Martin will also be thinking about a rocket propulsion in that case. This would be confining the plasma, but what if that magnet here is weaker than the magnet on that side? So now the plasma will find its way out in one direction, and that would be a rocket, a design of a rocket. So I think that the design can act both as a power-producing device as well as maybe a way of getting propulsion from fusion in general. And the Lockheed Martin company shows us their plans with that design. It's a very interesting situation, because it is not just governments like in the ITER project involved in that magnetic confinement, but also a private company. So they're talking here about their approach into building a compact fusion. That compact fusion can be used maybe, well, obviously for power production. The ITER device is 10 stories high. It's a huge in size. Lockheed Martin is thinking about a compact type of fusion reactor, and they are working on it today, in fact, and their hope is to contribute to global electricity demand by 2045. So if you find a way of interviewing as engineers with Lockheed Martin, oh, they have a fantastic new project. They're very innovative in their work. ITER and the demo can provide us electricity from direct fusion, but compact devices have a different field of application that they think that can contribute about 44 kilowatt hour, whereas the approach of ITER and the demo and the plants, the approach using the tokamak maybe or the stellarator would contribute 100 kilowatt hours by 2080. Lockheed Martin shows that they are more interested in providing power maybe for jets or for an aircraft carrier, but they're also thinking about producing electricity. Their compact devices can be carried on a trailer behind a large truck. So both the governments of the world are seeking magnetic confinement with large reactor systems, and private companies are also looking at it. So again, the private company is looking at compact systems, high beta. Beta is the pressure of the plasma. And you could see here that they're thinking about a fusion reactor providing power for an aircraft with 1, 2, 3, 4 turbofan engines and with a full fuel processor. So the hope of getting fusion is quite large and well established in the scientific and engineering community in general. Fusion research and development has thrown continuously new challenges to test the ingenuity and skills of at least 2 generations of scientists and engineers. The next step in magnetic confinement, the ITER, the International Tokamak Experimental Reactor, is essential to realize that key technologies of a future viable energy source and have to be operated successfully first. I'd like to point out here that in the development of this tokamak, they're using deuterium plus tritium as a fuel, and the tritium does not occur in nature. So it has to be bred, as we said, from lithium. So here we are facing a resource problem because lithium is a metal used right now in the transportation system in electrical vehicles for the lithium-ion batteries, and in other applications like batteries for computers and watches and phones and so on. That's one problem with the DT fusion reaction, and also using deuterium plus tritium. As you breed the tritium from the lithium, the breeding of the tritium is very marginal. Like you use a neutron, that would be the breeding ratio, and it's very close to 1. If you have an uncertainty of 20% in the production process, then it is very marginal. Hence, you need methods of avoiding the production of tritium, maybe by going directly to the DD cycle, the deuterium plus deuterium cycle. Then we would be burning literally water. Deuterium is a hydrogen isotope in water in general. Only then it will be possible to check with confidence the accuracy of the prediction of Arstimovich. That's the grandfather of the tokamak concept, a Russian scientist there, who said in 1972, we quote him saying, "Fusion will be there when society needs it." So that is the way to conclude the chapter on fusion in general. Progress has been occurring. You notice even that most of the experiments, like the tokamak fusion test reactor, the doublet 3 or Alcator C at MIT, or doublet 3 again, or the JT Japan Torus 60, most of them used really deuterium because deuterium doesn't have the handling difficulties that we have with tritium. However, plasmas with tritium have been also tried. The TFTR initially burned deuterium, but then it turned into burning tritium. And the progress is moving, as you could see, towards our very famous Lawson criterion, when we basically can reach the megawatt level of production from a typical plasma. People think that by 2050, we would have an operating reactor at the 1,000 megawatt thermal power of the plasma. The suggestion again is that DT here has a problem, very marginal in terms of very marginal tritium production that should be surmounted. There are ways by multiplying the neutrons, maybe in beryllium or in lead. There are threshold reactions, end-to-end reactions, where a neutron is absorbed and you get 2 neutrons out of the reaction. Maybe going back to the DD reaction would avoid fully the production of tritium in first generation reactors in general. So here it is, the progress, the fusion power plant regime hopefully would be reached in some future times. following what's called Moore's law in semiconductor devices, is that the power that we get basically goes by a factor of 10 every 10 years. That's Moore's law. So fusion performance has been following the red dots. Moore's law in solid state devices has been following Moore's law. So if they move in the same direction, if progress in fusion appears and to follow the Moore's law of increasing the number of transistors on a computer chip, then maybe we'll have fusion in our lifetime. And there is a way of getting fusion in our lifetime by using a hybrid. And that would be the topic of the next chapter, looking into the future. I'll stop sharing. If there are any questions, to answer questions in the chat room, I'll be happy to answer any questions. Okay, so we don't waste any time. We go back into recording and the screen, and we get ourselves a look into the future. And a look into the future would be using, as I suggested, a hybrid, and not just using a hybrid here as a design, but also using a thorium hybrid. This is some material that you can find also in research reports that you can see on the main page of our website. I'll make the point at the end of the lecture, but thorium is another material that we can consider for producing, of course, fission energy. And the reason for it is that primarily really is that we have 4 times more thorium, or the abundance of thorium in the Earth's crust is 4 times that of uranium. And we wrote an equation, equation earlier that suggests that we can breed a fissile element, uranium-233, from thorium, which is 232. An interesting aspect of thorium is that it has only one isotope, thorium-232, in nature, all right? But it is an even numbered isotope, so it cannot fission, and we cannot create a critical mass out of thorium-232. So the usefulness of thorium is only if we have a source of neutrons, and that those neutrons will be used to breed uranium-233 from thorium. And that is some ideas that many engineers and scientists are adopting. You can go to the web and get more information and watch conferences, lectures from what's called the Thorium Energy Alliance, a group of scientists and engineers who are advocating switching from the uranium-238 plutonium fuel cycles in fission to the thorium fuel cycle. Here, I'm talking about a fission fusion, which we, in that case, call a hybrid. Why consider a hybrid of fission and fusion? In the diagram that I have shown you, we'll discover that we are a factor of 10 in the Lawson criterion from achieving fusion. So we need to produce a factor of 10 more energy that we are using to generate a plasma, whether it's inertial confinement in the laser and heavy ion beams, input energy, and or in the magnetic field and the ion beams and microwaves heating and the transformer action of magnetic confinement. So we are, according to Lawson criterion, or a factor of 10 away. How can we get that factor of 10 away? Well, we can get it through using a hybrid, not necessarily pure fusion. Why? If you talk about a hybrid of fission and fusion, you are using an optimal process. Fusion as using a if you consider fusion and you consider the D plus T reaction, you produce about 17.6 million electron volt of energy. That's a Q value. Let's say it's 20 million electron volt of energy per reaction, the DT reaction. The neutrons that come from fusion are at the 14.06 million electron volt. Well, let's compare this to fission. A fission reaction produces for us 200 million electron volt per reaction, compared to, say, 20 million electron volt only from fusion. But fission has a neutron energy of about 2 million electron volt in a fission neutron, whereas in fusion, it's 14 million electron volt per fusion neutron. So we can say that fusion is energy poor but neutron rich, and that fission is energy rich but neutron poor. And if you have a situation where you have a function in mathematics that's monotonically increasing and another function that's monotonically decreasing, when you combine them together, you can get an optimal combination. Hence, a hybrid would be an optimal combination of fission and fusion. In addition, we can apply this to the thorium cycle and use a resource that is available to us on Earth for an unlimited energy supply, practically in that case. A first generation thorium hybrid would use the DT fusion reaction as a neutron source instead of the isotopes uranium-235 or plutonium-239. A second generation now would use only the DD reaction. So in that case, you don't need to breed tritium. You use only deuterium from H2O or HGO from water. So we would be burning water, practically hydrogen, to produce energy. And the Earth is a water planet. 70% of the surface of the Earth is, of course, water. So we have an unlimited, practically unlimited supply of deuterium, which has an abundance of 160 parts per million in water from the world ocean. So every million molecules of water on Earth has actually 160 is a better, more recent number in the measurements in general. Either system could use the uranium-233 bred from thorium-232 for power generation. Another possible technological advancement would be to switch from the use currently of solid fuels into the use of liquid fuels. That has been an evolution in energy production in general when we switch from solid coal to liquid petroleum. Liquid that's petroleum is easier to handle than a solid. And in existing fission reactors, because we are using solid fuel, the fission products remain in the solid fuel and produce heat after we shut down the main chain reaction. And they were primarily the cause of the decay heat that we were not able to extract in the three main accidents that occurred in the fission field: the 3 Mile Island, the Chernobyl accident, and Fukushima. The three of them were related to the use of solid fuels where the fission products are still left in the fuel inside the reactor core. If you use a liquid fuel, like the evolution from coal to petroleum, then we can continuously extract those fission products and we eliminate the safety or the hazard factor that the use of solid fuels presents to us and the cause of the three main accidents in the nuclear industry. In that case, you may like to use a molten salt, and that's what we are going to talk about today. The molten salt would uses a liquid metal alloy. So it is not a liquid metal. It's a sodium salt with thorium, with fluorine and beryllium. Notice here's the thorium again. So in the way that we would be evolving into a more advanced use of nuclear fuels, because now you start by burning the producing neutrons that would breed uranium-233 from thorium. You introduce thorium as well as moving from a solid fuel into a liquid fuel. Beryllium there would be used as a neutron multiplier. Reaction of a neutron with beryllium produces 2 neutrons. So in that case, we don't run into the problem of the marginal production of tritium in the DT fusion cycle. So in that case, you gain a great advantage. And you also can think about using a fusion reaction that uses a DD plasma, even though a first generation may have to use a DT reaction in general. So in that case, a combination of the DD fusion approach, we wrote the DD reaction in the previous chapters, with the thorium molten salt, with breeding, well, provides us with an unlimited energy supply, with lots and lots of advantages that I'm going to show you later on. All right, so now let us look at the possible configurations of a future hybrid. A future hybrid would be a combination of a fusion reactor. Let's take first DT burning fusion reactor. And in that case, you'd have a fission component that is going to be now burning fission, uranium-233. So in that case, the fusion reaction would be fed by deuterium, that's from water from the ocean, and lithium. And as I said, it presents a resource problem because of the use of lithium in lithium-ion batteries that are used in the transportation system of electrical vehicles. The lithium would be transformed by absorption of a neutron from the DT reaction into tritium and fed into the fusion reaction. So now you have the deuterium plus the tritium reaction producing fission neutrons. Now, if you add to that DT fusion reaction a blanket that contains thorium-232, you can be now producing uranium-233. And that uranium-233 can be exported to fission reactors that would burn that uranium-233, which we know occurs in nature 4 times as much as uranium. If you input some lithium into the fission reactions, you'll find that you can also produce tritium, which solves the problem of the marginality of the production of tritium from fusion reaction. So that's an optimal system that really would be feasible. As a first generation, you burn deuterium and tritium, you have to deal with the lithium. Once we learn more about how to build fusion reactor using the first generation DT fusion reaction, we can now evolve into using the catalyzed DD fusion. And we wrote about the use of deuterium. So now you don't need that lithium input. You don't need to produce the tritium. All you do is feed the catalyzed DD reaction in a fusion reactor with deuterium from our oceans, from the water. You separate it through distillation or through electrolysis. And you add also now thorium-232 that would absorb the neutrons from the DD catalyzed fusion reaction to produce uranium-233 that you take in satellites that would use that uranium-233. It's a simpler system, but you need to be able to operate with the DD fusion reaction. So we have 2 choices here. Again, I emphasize that thorium is much more abundant than uranium. It has other advantages that I'll show later. For instance, in terms of proliferation, if you produce uranium-233 from thorium, you find that you get uranium-232, and it's very hard to separate the uranium-232 from uranium-233. Uranium-232 decays into thallium-208, which is a very powerful gamma emitter. So uranium-233 as a fissile element is unsuitable for making weapons. So that contributes to peace in the world and uses nuclear energy for basically aggressive purposes. This is a picture of thorium. Thorium, as I suggested, that's thorium dioxide, very common element. And it has been used actually in the mantles of incandescent gas lanterns, because sodium dioxide can take extremely high temperatures. Some people still use those sodium dioxide mantles for camping lanterns in general. The thorium fission fuel cycle was investigated thoroughly in the period 1950 to 1976 in what was designated as a molten salt breeder reactor at the Oak Ridge National Lab, and there was a pilot plant built there along this line. Thorium has been also investigated in one of the very early reactors built by the United States, the second reactor to produce power in the world after the Calder Hall reactor in the UK that was the first to produce nuclear power. The Shippingport fission reactor also was a replica of a naval reactor design used for propulsion for submarines and aircraft carriers. So it has experience from naval propulsion in general. The Shippingport reactor, I'll show it to you in a moment, operated for 5 years on a single load of fuel, and it did breed uranium-233 from the thorium-232. The existing uranium-233, uranium-235 fuel cycle have been favored just for historical reasons. The historical reason is the need to produce plutonium for weapons. So the uranium-238 plutonium cycle is more like a weapons-oriented cycle. The thorium one would have could have been used, but the need to produce plutonium for the nuclear weapon states is the reason that we have the uranium-plutonium cycle in our hands right now. The availability of uranium enrichment capabilities, you'll find that the uranium capability, instead of enriching uranium, it can be shifted into uranium-233 production. In fact, the United States produced most of its fissile plutonium as well as fusile tritium in heavy water reactors that were operated at the Savannah River using highly enriched naval reactor fuel and the lithium aluminum alloy, where the lithium would absorb the neutron, produce tritium for thermonuclear devices in general. India doesn't have resources in uranium, but it has large resources in thorium. So they have a plan. In the first stage, they'll use heavy water reactors fueled by natural uranium, as well as light water reactors. And the second stage, that plutonium that would be produced in those heavy water reactors would be used to get a start of fuel for a liquid sodium cooled fast reactor. And in the third stage, they have a very long range plan. I think India, as an old civilization, does not think in terms of quarters or years like in the economies of the West. They're thinking more along hundreds of years of development of the nuclear energy. In the third stage, that uranium-233 would be produced by capturing neutrons in thorium-232 from fast reactors. And we know that with the thorium cycle, you can use now high temperature gas-cooled reactors. They do not mention the production of hydrogen as an energy carrier, but of course, high temperature reactors would have a higher efficiency than the existing light water reactor. So India is developing the advanced heavy water reactor using low enrichment uranium at 19.75% uranium. Why is that? In the United States, we are using only 3 to 5% enrichment by some kind of a decree or by a requirement that was set up by Admiral Hyman Rickover, who was, of course, the pioneer who started the nuclear navy. And he just didn't want to have the highly enriched fuel from 68% to 90% used in naval reactors circulating among people and countries. So he set up that criterion of 3 to 5% enrichment of the fuel. And it has stuck there without anybody questioning why is it that it has a light water reactors, the boiling water reactor, and the PWR must use lowly enriched fuel. The size of the reactor in that case becomes huge, whereas if you go use high enrichment, then the size of the reactor would be minimized to the level, to the size of naval reactors in general. The International Atomic Energy Agency suggests that for peaceful applications, we should not exceed the 20% enrichment for uranium-235 for reactors. Being aware of that limitations, India, in their light water reactors, are smart enough to avoid getting to the 20%. So they chose 19.75% exactly, so that they do not exceed the 20%. But our light water reactors should be really within the range where you cannot develop nuclear weaponry from the enriched uranium. At 20% enrichment, you cannot build an efficient device in general. So India has a plan of over 100 years into the future of progressing from the uranium-plutonium cycle to the thorium cycle. So you could see here that with this idea of the hybrid and with the idea of using liquid fuels instead of solid fuels, this is the future of a smart kind of approach to nuclear energy generation. Okay, let's look quickly at the history, because history determines for us where we are headed into the future. The thorium cycle, as I suggested, the idea of breeding uranium-233 from thorium-232 is as old as the development of nuclear energy in general. And it was used in the shipping port pressurized water reactor. And that reactor was a pressurized water-cooled reactor as an imitation of naval reactors that use very highly enriched fuel in that case. And so the pressurized water reactor, as you could see here, this is an actual picture of the reactor. It was the first commercial and experimental nuclear power plant in the United States, second to what the UK produced electricity at the reactor at Calder Hall. It was cooled with carbon dioxide in that case. It first operated in 1957, was the first United States commercial nuclear reactor operated to produce electricity by the utility Duquesne Light Company. The UK's Calder Hall dual-purpose pressurized CO2 cooled pile, dual-purpose because the British found that Russia and the United States had developed nuclear weapons, and they couldn't stay there as a large power. So they built the Calder Hall reactor as a dual purpose, produced both electricity as a source of income, as well as producing plutonium, and it was gas cooled using CO2 cooled reaction. That was at C-scale, Cambria. It went critical in 1956. The shipping port plant shown here was a pressurized water reactor with the first two reactor cores as seed and blanket cores. What's a seed and blanket core? You could see here that they are lowering a core that would contain uranium-235 initially. The blanket would be containing thorium-232. Actually, the thorium-232 was in the control rods themselves, absorbing the neutrons and producing uranium-233. So there is experience with the thorium cycle. This is how the fuel looked like. It was not the cylindrical rods that we use in present day pressurized water reactors. It was plates, a plates type of a fuel. You would have the fuel here plated on both sides with a zircaloy, a zirconium alloy. Zirconium resists corrosion, as we know, as well as does not absorb neutrons appreciably. And this is a fuel that is in fact used in naval reactors. So it got the experience from naval reactors in general. This is a subassembly. The subassemblies were in the core, shown here with this, is the same geometry as existing PWR. So in that case, you find this is the reactor core here. This is the seed or blanket region, as it said, seed region, where you place the thorium-232 to absorb the neutrons from the core and turn into uranium-233. It performed nicely, but they kept replacing the cores with different configurations. Eventually, they adopted the rod configuration rather than the plate configuration, but this is the blanket type of an assembly in general. All right, so the use of thorium has been introduced in the shipping port reactor, and other most of the gas-cooled reactors experiments or pilot plants also use thorium. The use in thorium for in the future is considered possibly in the use of gas-cooled reactors, the high-temperature gas-cooled reactor. Shown here is little tiny grains, I would say, of thorium or uranium surrounded by layer upon layer of pyrolytic graphite and silicon carbide. You know that silicon carbide is used in the plates of the re-entry vehicles on the international, say, space station. It can take very high temperatures. A layer of graphites would contain any fission products inside that little grain, the size of 1 millimeter, maybe the size of a grain of salt or a grain of sugar. Then each one of those would be placed as in a larger container, a graphite. And you know that graphite can take very high temperatures. Hence, we can operate a high temperature gas-cooled reactor, maybe using helium as a coolant, and attain very high temperatures. That would be the ideal way to produce hydrogen for a future fuel cell kind of transportation system, where fission energy has its energy stored instead of in batteries like the lithium chemical batteries, like lithium-ion batteries. It would be stored in hydrogen, and then hydrogen would be used in conjunction with fuel cell to produce electricity for electrical vehicles in a future transportation system. Two forms of that fuel would be used. One of them would contain uranium-235 as a source of neutrons, but then some of those other particles here in the fuel spheres, as they're called, would contain thorium. And that would be they name it the triso fuel. The uranium dioxide fuel kernels would be 0.5 millimeter, half a millimeter in diameter, so that you could see how small they are. They're enclosed in layers of porous carbon buffer zone, an inner pyrolytic carbon zone, and then you have that silicon carbide that can take very high temperature, and another layer of pyrolytic carbon. A combination of the triso and biso fuel. This is a biso meaning, well, that's contained uranium. This one, triso, would contain thorium. That would be a diameter of 0.9 millimeters. So it's only about 1 millimeter in diameter. They're all enclosed in a larger ball or a pellet. In that case, that would be 60 millimeter in diameter. The graphite there, 5 millimeter graphite layer, and those coated particles are embedded in a graphite matrix. Those fuel spheres would be the size of tennis balls. In fact, here they are stacked, and they became the basis of pilot plants that were named the pebble bed modular reactor. So in the United States, that type of a fuel was used in a reactor, the Fort St. Vrain. It was gas cooled and it used thorium. However, and it operated in the United States in Colorado. A problem happened in the turbine part of the plant, so they simply shut it down and then restarted the whole thing using coal. So we lost the opportunity of introducing the thorium fuel cycle because of a problem in the turbine part of the plant. So in that case, still the idea is alive in what is called the gas turbine modular helium reactor shown here. In that case, you would have two parts in the plant, the steel reactor vessel. And because ideally when you use a gas, we said that earlier in previous chapters, you'd like to use the Brayton cycle or a gas-cooled cycle. They show us here the compressor that would implement the Brayton cycle. So that is the gas turbine modular helium reactor. Would be using two parts, a part for the reactor and a part for the compressor, and get the advantage of both a very high efficiency because we are operating at high temperature in the graphite, as well as breeding in the thorium cycle. But that's a solid fuel. So people have thought about the even using liquid fuels, as I'll show you in a moment. Experiments and pilot plants have been built. This is a plant of what's called the integral type. You have a pressure vessel here. You have your pebbles here that look like tennis balls dropped from the top into a hopper. And as they burn, they are extracted from the bottom. So that would be an online operating system. You circulate the gas in that case, but into the pebble bed and send it to the compressor if you use the Brayton cycle. That would be the case when you use the gas turbine cycle here because of the existence of the compressor and the recuperator. This is a Brayton cycle. However, the Germans built a pebble bed reactor, but they did not explore the idea of the gas turbine cycle. They simply cooled the system with water. They took it to a steam generator. Actually, they used the gas here, but they cooled, send it to a steam generator, produce steam. The neat aspect of the design is that the steam generators are not connected to the core of the reactor through piping. So they eliminate the possibility of, say, an earthquake breaking the piping and losing the coolant in general. So you could see here, they use it to produce steam, when in fact it would have been a better approach to use a gas turbine type of a cycle. All right, so this reactor used the thorium in the fuel and experimented with the breeding with the thorium reactor. Another interesting innovation that was done in that reactor is the way that the way that they cooled the coolant or ejected heat to the environment. Other approaches that were planned but not applied was to build actually a pebble bed reactor, gas-cooled reactor, in a big hole next to the Clinton plant west of town here. It was meant to have 2 units, but they only built 1 boiling water reactor. The idea was to use there in that single hole in the ground a pebble bed gas-cooled reactor. It didn't happen. This is the pebble bed modular design that was suggested in South Africa, designed by South Africa. The reactor core would be here. The generator would be here with a gearbox and a turbine. And if you see that compressor here, it tells you immediately it is a gas-cooled system with the recuperators and using the Brayton cycle. That was the idea of using gas-cooled cycles with a pebble bed system, and the pebble bed is planned to be used with the thorium as a fissile fuel. So the Germans also built a second reactor using thorium, a pebble bed system. They named it the THTR 300 pebble bed reactor, 300 for 300 megawatt electric. And the interesting innovation there is that for the cooling tower, instead of using water-cooled towers like this one, cooling tower, you could see the steam coming out there, they use metallic towers. So in that case, they don't need water. And if they don't need water, you can build those reactors in arid regions of the world, say in a desert area, where you don't have water. And in that case, it's just an empty shell here, where the coolant from the reactor is rejecting the heat to maintain the flow system from a high temperature reservoir to a low temperature reservoir that we were introduced earlier on. You could see that it burned uranium-235 to breed uranium-233 into thorium-233. This was a 180-meter high cooling tower, metallic, that doesn't use water for cooling in general. So we have some experience with the thorium cycle that may be the basis for future hybrid reactors. We are talking about the hybrid here today. The high temperature engineering test reactor now still exists as a pilot plant. This one exists in Japan, the Japan Atomic Energy Research Institute. JERI is having a pilot plant of 30 megawatt thermal prismatic core. The core looks like the one used at in the Colorado HCGR in the United States. And in that case, you have a prism, a graphite prism with holes in it. The holes contain pellets of the high density pyrolytic carbon and silicon carbide. Again, low density fuel, but in the form of a cylinder rather than the sphere of the pebble bed. And then you have other holes. So the fission occurs in those pellets. The energy, the heat is transferred to the graphite, and then you circulate a coolant there, and you can reach temperature of 950 degrees Celsius. Compare that to, in the graphite, compare this to the 350 degrees Celsius that you get in light water reactors, and you immediately find that you're opening a new realm of energy production. High temperature means high efficiency, and second, you can use it in thermochemical processes to produce hydrogen for transportation fuel. So this is the JERI high temperature engineering test reactor, an outlet coolant temperature of 850 degrees Celsius and a maximum of 950, almost 1,000 degrees Celsius. It is emplaced underground below grade level, as you could see here, for an added level of safety. All right, now China also has a pilot plant, the HTR-10. I have shown you more detail about it in the chapter on gas-cooled reactors, a high-temperature gas-cooled reactor. This one uses a pebble bed, like those pebbles that were used in the THTR in Germany. It's a 10 megawatt thermal. It's operating at Tsinghua University in China. And again, the idea is to develop the Brayton cycle or gas-cooled cycle. The interesting aspect of using thorium leads us to an evolution, future evolution that is needed in the fission field, in that we should do the same, follow the same evolution or progression that where we produce steam or power from a liquid rather than a solid. In that case, a solid would be coal, but we know now that boilers, most boilers in ships, for instance, at least ships, would use a liquid fuel oil rather than coal. You don't need the people with shovels shoveling coal into a boiler. And in that case, as I suggested, what is being considered is a molten salt. It's not a liquid metal, it's a molten salt as a combination of beryllium fluoride, thorium-232 that gets converted into uranium-233 fluoride, and lithium fluoride. If you use the lithium here, lithium-7 instead of lithium-6, in a thermal neutron spectrum, it does not produce appreciable amounts of tritium. If you really want to produce tritium in a hybrid type of a configuration of fission and fusion, you replace that lithium-7 by lithium-6. So you could see here, it's a salt that's a fluoride, lithium fluoride, beryllium fluoride, uranium fluoride. The combination of the three is solid at or a crystal at room temperature. When you heat it, it becomes a liquid as a coolant, but then you start your cycle with thorium-232. As you irradiate it in a neutron flux, it turns into uranium-233. So it's a use of thorium as a form of a liquid. A double innovation in the sense that you are replacing a solid by a liquid and using thorium for breeding in general. In that case, this is in fact a suggestion for one of the fourth generation reactors, the molten salt reactor. Here you have now a salt circulating as a liquid in a matrix of graphite. And you see here the turbine and the generator, but then you have the compressor on the same shaft as the turbine. So in that case, it's using the gas turbine cycle, higher efficiency, the possibility of breeding, higher level of safety, higher temperature so that you can produce thermochemical processes to produce hydrogen. Instead of producing the steam and electricity here, you can take some of the high temperature steam to a hydrogen production plant. One aspect of the safety there is that if for any reason you lose your pumping and you dump the fuel, actually by having a freeze plug, the chain reaction stops immediately. So it's a very safe reactor. Just emptying the fuel, you can leave it overnight, since you would be removing the fission products continuously. So the decay heat that caused the three main accidents in the nuclear industry possibility would be eliminated in that case. The 3 Mile Island, Chernobyl, and Fukushima all occurred because of the use of the solid fuel where the fission products were kept there producing heat even after the main chain reaction is stopped. So that's basically one way where we can get innovation in the nuclear field by using liquid instead of solid fuels, increasing the levels of safety several fold, and also breeding in the thorium in the molten salt. That is also provide us with a practically unlimited energy supply. So that is the use of thorium and liquid fuel. In the case, of course, of, as I suggested, the use of the DT fuel cycle as fusion in a hybrid, you find that tritium does not occur in nature. So we need to use the neutrons from the DT reaction here, let it interact with the isotopes of lithium, lithium-6, and lithium-7 to produce tritium. The first reaction with lithium-6 is a thermal neutron reaction. The neutrons are thermal. In that case, you get tritium and the positive Q value energy is released from the reaction. However, the neutrons interacting with lithium-7, which is the main isotope in lithium, yes, they produce for you another neutron, a triton, but the reaction is endothermic. See, it absorbed some energy from the process, half the energy produced from the lithium reaction. So in that case, what we would like to think about is a salt that contains lithium fluoride, beryllium fluoride, and thorium fluoride as a coolant. The thorium-232 will absorb a neutron and produce uranium-233. So it's a combination, the salt. It's not a metal, by the way. I emphasize this. This is a salt, lithium fluoride salt, beryllium fluoride salt, and thorium fluoride salt. The beryllium is a neutron multiplier. It provides you with more neutrons that can breed more thorium, uranium-233 from the thorium. For a practically unlimited supply of deuterium from seawater at 150 parts per million, you can adopt the DD fusion reaction. And in that case, you can produce both uranium-233 and you can burn deuterium from the ocean as a hybrid. And we suggested that would be an optimal combination. If we cannot have that D-helium-3 reaction occurring in the catalyzed DD reaction shown here, by the way, you cannot have just a DD reaction without getting the tritium to interact with deuterium and immediately fusing, because the cross-section for that DT reaction is higher than the cross-section for the DD reaction. So the three of them have to be occurring together. The D-helium-3 reaction needs a higher temperature of the plasma. So if it doesn't occur, we get what we call the semi-catalyzed DD reaction. Catalyzed because you could see here that the helium-3 and helium-3 cancel out from both sides of the balance equation. Tritium and tritium cancel out. So in that case, we have a system where tritium and helium-3 act as catalysts. This is a semi-catalyzed where the last reaction is not there. It still produces positive energy. It still burns 5 deuterons, producing an alpha particle, an alpha particle, which is helium-4, an isotope of helium-3, and a proton plus 25 million electron volts of energy in that case. In the case where you don't need to breed tritium, where you use the DT fuel cycle, you can replace, in fact, we did calculations on this and proved that it is feasible. You can replace that tritium with sodium. So it overcomes the resource problem and needing to have lithium available to us in competition with electrical vehicles and other consumer products using lithium-ion batteries. All right, so that salt would have a density of 4.5 gram per centimeter cube. It has a high density, so it would have also some good thermal conductivity in general. All right, let us think then about combining fusion to fission in a hybrid. As I suggested, that would be an optimal configuration. We did calculations. We find that the data here are really from some work that I contributed to a larger project. Here is the design, the materials used in a fusion fission reactor. The plasma would be the first zone with a diameter of 100 centimeter. We are considering using a laser beam in an inertial confinement fusion reaction producing neutrons for us. We used the two possible fusion fuel cycle, the DT burning fusion cycle, producing 14.06 million electron volt neutrons, or if possible, the catalyzed DD reaction, which produces 50% of the time in the 2.45 million electron volt neutrons and 50% of the time a neutron from the DT reaction. The first wall of the inertial confinement laser fusion reactor would be made out of 316 stainless steel, and we use a coolant to cool the blanket beyond the wall. The molten salt that is used in that case is lithium fluoride, beryllium fluoride, 3-fluoride, thorium fluoride. Notice here that we are breeding now uranium-233. In the case of using the DT reaction, we use a lithium fluoride. In the case where we use a catalyzed DD reaction, we don't need tritium. So in that case, it becomes sodium fluoride as a component of one of the fluorides in the salt. Notice that the molten salt is a combination of 3 fluorides: sodium fluoride, beryllium fluoride, thorium fluoride. Thorium to breed uranium-233, beryllium as a neutron multiplier, and sodium as a way of cooling the system in general. The structure was type 316 stainless steel. We need a reflector, as I'll show you in the geometry. Graphite was used as the reflector in general. And this would be, if you are designing or building such a reactor, you calculate the number densities of all the components, the isotopes that are used in your model. So that would be a neutronics type of calculation to estimate whether we can breed uranium-233 from thorium-232 and by how much, quantify it, and whether we can breed tritium in the case of using the DT reaction. If you use a lithium fluoride, beryllium fluoride, thorium fluoride salt, you'll find that you can calculate the number densities from the proportions, the percentage of each one of those elements at a density of 4.52 grams per centimeter cube. So now you break down the isotopes for their cross sections: lithium-6, lithium-7, beryllium-9, thorium-230, and fluorine-18. If you do not use lithium fluoride because you are not using the DT reaction, you replace the lithium by sodium fluoride. In that case, you have the elements, the isotope sodium-23, beryllium-9, thorium-230, and fluorine-19. Stainless steel as a structural material contains 64% iron, 18% chromium, 13% nickel, 2.6% molybdenum, 1.9% manganese, and 0.98% a combination of silicon, titanium, and carbon. And you can go and calculate the number densities, nuclei per bond centimeter. Why do you calculate those number densities? Because this would be multiplied by the cross sections at different energies, giving you the macroscopic cross sections in the calculations in general. Graphite as a reflector has a density of 2.25 grams per centimeter cube, and water as a coolant of the blanket of, obviously, we are using here room temperature 1 gram per centimeter cube. And the question now is whether we can operate such a hybrid that would breed both the tritium and the that would breed both tritium as well as uranium-233 from thorium. Let me just show you why very quickly. The salt contains beryllium. Beryllium has an interesting property in that it has a threshold of about, say, like 2 million electron volt here, the cross section, where you get an N-to-N reaction. And in that case, when you see that's N-to-N, meaning that the beryllium absorbs a neutron and gives you back 2 neutrons. So in that case, those neutrons are available for the breeding process, either to be absorbed in lithium to produce tritium in the DT cycle, or absorbed in thorium to produce uranium-233. You could use bismuth-209. Also, it has a threshold for an N-to-N reaction, and lead. And this is the configuration of that fusion reactors. You would have a laser beams coming from the walls in a container in the shape of a cylinder. And you'll get here pellet micro explosions at the center. You could feed pellets that would generate a DT reaction. Then you have 14 million electron volt neutrons. Now on the top and the bottom, you have a blanket that would absorb the neutrons and breed, as well as in a DT system, you breed tritium or breed thorium from uranium, or breed uranium-233 from thorium. The interesting aspect of that design is that it was designed to have in the radial blanket, all around the radius here, fuel elements that would contain thorium. And as the thorium-230 there absorbs a neutron, it generates uranium-233. So the idea here was to build it as a way of enriching fuel elements for pressurized water reactors. Here you are 3 of those fuel elements on top of each other, where thorium is thorium dioxide, and then it turned into uranium-233. Then you take those fuel bundles and burn that uranium-233 in a fission reactor. So in that case, the fusion reactor becomes a fuel factory for existing PWRs burning. Instead of burning uranium-235, that would be burning uranium-233. So if you look at the configuration, You'll find here now it's a bundle of 17 by 17 thorium dioxide now, pellets for inclusion in a fission reactor. Each one of them would have basically a thorium dioxide pellet surrounded by cladding and surrounded on all sides with tubes that contain, in that case, lead. Why lead? Lead, like beryllium, has an end-to-end threshold reaction. It absorbs a fast neutron, like from the DT reaction, or the DD reaction, and produces for us generates a second neutron. So it's a neutron multiplier. So the fuel elements here for the PWR are surrounded on all sides by a lead producing extra neutrons. Then the surrounding lead around the fuel component here is followed by lithium. In that case, this would be lithium filled rods where if you need to breed tritium, the reactions from the DT neutrons or DD neutrons will produce tritium for you. So it becomes basically a fuel factory here, if you want to call it, or an enrichment factory where you enrich pressurized or boiling water reactors fuel elements with the isotope uranium-233 from thorium-232, but the neutron source would be from fusion reactions. The calculation and models is shown here. Guess what? Your teacher here has carried out those actual calculations. So you'd have a neutron source at the center here. It could be either a tritium source from DT reactions or a neutron source from DD reactions, not as asymmetrical. There is not a symmetry there. This would be the first wall. This would be half a fuel assembly. And then you have the region of lead first wall, lithium reflector. And then at the end there, you have also a graphite reflector. The neutrons are emitted here in all directions. And because it is three-dimensional in nature, the neutronic model that is used uses Monte Carlo methods. So that we use the code called the Morse from the Oak Ridge National Laboratory to build a model first, a very complicated three-dimensional model here, but this is a fuel cell that occurs all the way around the periphery of the reactor. And the idea was to estimate, is it possible to enrich fuel in uranium-233 while at the same time producing tritium? This is the plan of the fuel cell in the plane. This would be the fuel element here surrounded by cladding. This would be a graphite reflector. That would be a region containing lithium for breeding tritium, and the neutron source generates neutrons that interact with the whole geometry. These would be reflecting walls because of symmetry that unit cell repeats itself in the whole geometry. It's a three-dimensional geometry. In that case, the only method in neutron transport is the Monte Carlo approach. Again, this is the compositions, but this is the important result that we get in that case. The question is, can we enrich the fuel in that case if we use the TT as a DT reaction? You'll find that if we are optimizing it with the region that contains the lithium, doubling the thickness and tripling the thickness, you'll find that as you double the thickness, the tritium production goes up per source neutron. And if you are at 1 or 2 optical thicknesses, which would be one total mean free pass, you are not producing enough tritium to get the chain reaction, enough tritium to proceed with the DT reaction. Only when you have enough of a thickness of lithium here, you have a breeding ratio of tritium of larger than 1. And that is the important aspect of the optimization process of the design. As you have neutrons producing more tritium, your absorption in the thorium to produce uranium-233 obviously decreased. And at the thickness of the lithium, you'll find that the combined tritium and the thorium N-gamma as a precursor to, of course, the thorium producing uranium-233, you are producing 1.5 basically combined tritium and thorium. So this tells us that yes, we can breed tritium from the DT reaction, but you could see here that the production is very, very marginal, 1.1 maybe, less than 1.1. And look at the error bars here. The error bars could be less than the one needed to proceed with the DT reaction. So in that case, you try to use the DD reaction, and in the table, we see that you can, in that case, breed enough tritium to proceed. If you don't need to produce the tritium, the DD reaction becomes the optimal way of using such a configuration for a future hybrid reactor, which becomes, in fact, a fuel factory or an enrichment factory. And here is a table that shows us the actual result. This is a case where you use a lithium, beryllium, thorium, fluoride, salt. And this is the case where the lithium now is replaced by sodium. So in that case, you don't need really to breed the tritium, and all the reactions now go to the production of uranium-233. Definitely, because the tritium production is very marginal, that favors the idea of using the DD fusion cycle. And that's emphasis that should be in fusion research. Engineering-wise, producing the tritium is very, very marginal. You need to use neutron multipliers, either that we use, in that case, beryllium, or you use lead. In that design, we used lead. Very quickly, what are the advantages of the thorium fuel cycle? It's an expanded nuclear fuel resource. Thorium is 4 times more abundant than uranium. It has a lower nuclear proliferation concerns, a superior system for handling the fission products, and you can separate at lower volume the short-lived isotopes, and it can achieve a higher burnup and fuel utilization than the uranium-plutonium cycle. So it has advantages if we can generate it, and this is really the regeneration factor as a function of the neutron energy. For the uranium-233 fuel cycle, you could see that we can produce enough tritium, we can breed in uranium-233 above the regeneration factor number of 2 at both thermal energies as well as at fast energy. And I discussed the non-proliferation characteristics, and I would like to conclude just by showing you the abundance of different isotopes in nature to convince you that, in fact, we can proceed with the thorium cycle. The dosimetry are fine, and this is the composition of fuels in the uranium and thorium fuel cycle. I invite you to read about it, but the last thing I want to show you is, okay, well, such an alternative sustainable paradigm or architecture would provide many advances in nuclear power generation. First, the breeding in the thorium fuel cycle. Thorium is more abundant than uranium, I repeat this. The possibility of using the DD fusion reaction, and the switching from solid fuels into liquid fuels in general. I invite you to read the chapter, and I'll remain in the chat room for any question, and the class can be dismissed. Thank you very much, Alvaro, for helping keeping the system operating efficiently.